99% of the blockchain developers out there don't know how the EVM operates under the hood. Now, there is a fair reason behind that because the content that is explaining the EVM stuff is so complex for people to understand that they give up. Understanding how EVM operates at the bytecode level or in the layman terms will be really beneficial for you if you are even getting started or a blockchain developer with some years of experience, or you are trying to get into the field of web3 smart contract security. Now, you probably want to be in that 1%, beating all the 99% and grasping the potential knowledge that others lack. This will help you do your job better and earn more money as a blockchain developer. Hello everyone, this is EVM Masterclass on Blockchain Ninja, and in this series, we will talk about the inner implementation details of EVM. We will start from really surface level stuff like a layman. We will see what a VM is, then what is EVM, then how the transactions are executed, what are gas, what are the different data storage methods that are used by EVM, and something like that. And then we will talk about the opcode level implementation, the opcode level translation of the Solidity smart contract code, and we will actually have a live website for it, that is evm.codes, and we will have a live streaming, and we will actually explore how the different opcodes work. Now, this is the part one, and in this part one, we will talk about what is VM, what is EVM, understanding EVM as a layman, how transaction is executed on EVM, accounts in the EVM, what are the different data storage methods, understanding gas, and exploring message calls types. Now, without further ado, let's quickly go to what is a virtual machine. Now, you might have heard about it, but let's suppose that you are a layman and you don't know what virtual machine is. Let me explain it to you. Virtual machine is a machine that is virtual. It is a simulated computer environment. A computer that is not in front of you in the physical form or hardware form, but it looks like one, and it is actually located at some other place. So, simulated computer environment, it is independent of computer systems. So, whatever the program, whatever program is written on a virtual machine, it can run on independent computer systems. Let's say, I write a program on Java. So how Java operates is, Java has a virtual machine, JVM, Java Virtual Machine, and whenever I write a program on Java, it compiles down in a way, and it works in a way that the program on Java can run on both Mac, like Apple's computer, or Windows computer, or Linux computer if they have the JVM, compatible JVM. Now, let's not quickly go to the details of JVM, but actually let's quickly see what is EVM. Now, before that, let's see what are the two types of virtual machines. One is register based and other is stack based. Now, down here, we can see that what is EVM? EVM is short for Ethereum Virtual Machine. It is a stack-based virtual machine. It means that the computations are stored and operated using a stack. We will see what a stack is in a bit. And what is EVM actually? It is a stack-based VM, and it is used to run smart contracts. Now, this is so much for you, maybe, but let's understand it as a layman. Let's say you are a 10-year-old person, and I'm explaining to you. So you can view it, EVM, as a program that is running on a lot of computers. Now, even this would not be clear to you, let's take the example of vending machine. Now, Bob, as a person, want to have lays or anything. He actually presses some button and gives a command to vending machine and says, "Give me lays." Now the vending machine does some processing and it gives him lays, right? In the similar example of Ethereum virtual machine can be regarded as a smart contracts vending machine, where instead of Coke, Pepsi, and Lay's and biscuits and all that stuff, we have different smart contracts. Now, Bob can either read the data from these smart contracts, or he can write the data to these smart contracts. Now, whenever the Bob wants to read the data, there will be a transaction, but that will be a read transaction. But when Bob wants to write the data, it will be, the so-called real transaction on the blockchain that will actually change the data on the blockchain, and that can be regarded as a state changing transaction. Now, let's see how the state changing transaction is executed on EVM. Let's say Bob or you as a user wants to read from the EVM. If you want to read the EVM, this EVM state will be used and this EVM state will be returned to you. But if you want to write into the EVM, a transaction will be initiated and the EVM actually performs some state changes. For example, let's say there was a variable counter 1 and I wanted to change it to 2. Now, there is a whole lot of changes that has happened in the EVM, and in the result, there will be a new version of EVM that will be updated with EVM. Now, all the computers on the network has this old version, right? But this new version has to be verified and copied to every node or every computer on the network. So there is actually a process called consensus algorithm. We will explore it in detail in the next videos, but with some algorithm, with some steps, this updated state of the EVM will be copied to the different computers. Now, this was about understanding what Ethereum virtual machine is. Now, in a short note, Ethereum virtual machine can be regarded as a giant computer that is running globally, and it has different smart contracts and different accounts, and and that is machine independent. You can read from it and write for it, and that is not machine dependent because it is not running on any machine, but it is distributed. It is running on a lot of machines. That is why it is decentralized, because there is no central party that is holding the Ethereum virtual machine. So no one owns Ethereum virtual machine. Ethereum virtual machine is owned by shared people. Okay. Now I hope this will make sense. Now coming to the second part of the video, and for this part, if you have any confusion, just hit down in the comment and write it down there, or you can ask me on LinkedIn or Twitter for explanation. We can have a chat and clear your confusions, because at the end what matters is how clearly you can understand the concepts. Now let's quickly go to the accounts. So Ethereum has this interesting thing called accounts. So in the account, we have the balance of the account, we have nuns, the number used only once. It denotes the number of transactions that this account has done. And if, let's say, I have done 2 transactions and I want to write another thing to the contract, let's say counter was 1 and I want to update it to 2, like any change on the blockchain, there will be another transaction. So my nuns will be incremented to 3. So nuns is incremented after every transaction, that is the right transaction, right? Now, for every account, we have a balance, we have a nuns, and we have some storage, and we have some code. Now, what this storage and code does? So essentially, an account has 2 types. On EVM, we have 2 types of accounts. One is externally owned account, that is owned by a human or a person outside of the blockchain, that is controlled by a private key. So they can sign the transactions with a private key. If a person does not have the private key, they cannot sign the transaction with that account. Now, for this EOA, we only use 2 fields, balance and nuns. For this, the storage field and code field is empty. Storage and code field is used by contract account. Now, what is a contract account? If a smart contract is deployed on blockchain, it is by default by default assigned an account, right? And inside the or actually the smart contract is an account on a blockchain. And how the block how blockchain actually represents this account, it has some balance. We can send some ether to this contract, and it has the nonce, how many transactions the contract has uh, done till now, just like EOA. And we have a storage. So every smart contract has a storage. We will see in a minute why. And we have code where the entire logic of this smart contract is actually stored. Now, smart contract or contract account is not controlled by a private key. Rather, it is controlled by the contract code. And the contract code does not execute it by itself. Someone has to make a transaction to trigger a function call and perform some transaction. Now, let's quickly go to the data storage in EVM. This is my favorite part in EVM, and I've invested a lot of time here. So there are six types of methods in which we can store the data in EVM. One is stack, the other is memory, call data, storage, logs, and code. Let's quickly go over each. The first one is stack. So a stack, what is a stack? Stack is just a pile where multiple things can be put on one another. Let's say this is an empty stack. I actually push one item here. It will have this one item. When I push two, there will be another item on top of it. And there will be when I push three, there will be another item on top of the second one. You will see a pattern here. The pattern is last in first out. So the item, if the item comes before everyone, it will actually be taken out after everyone. Let's say the one was pushed before everyone, and one can be only taken out after everyone is taken out, right? And the pop what the push does is it actually takes an item. The item can be anything, takes a number or item, and it pushes the item on top of the stack. And what does pop does, the pop actually takes the item out of the stack on the top. And this was about data structure of stack. And I hope you already know about stack, but in the case you don't understand, I needed to explain it. Now, here is the interesting part. EVM uses 32-byte words or slot standards to represent values. So inside EVM, almost everything is dealt in 32 bytes standard. So let's say I want to store one. How the one will be stored? The one will be stored like uh, 0000. There will be 63 zeros and 1. Now let me tell you why 63 zeros. So let me actually I can't have another thing. Okay, so what is 1 byte? So 1 byte is 2 digits. Let's say 00, and each digit is composed of 4 bytes, 4 bits, right? And 4 bits and 4 bits is equal to 1 byte. So when I have 2 bytes, number of digits will be 4, right? So when I have 32 bytes, the number of digits, just take a look, the number of digits will be 64. Just double it up, and 63 of them will be zeros, and one will be the another digit, right? And that can be seen here. Just a minute. Yeah, you can see we have here 63 zeros. You can count it, and we have one here, right? Now if I want to actually denote 2 in the hex and also in the EVM, we deal everything with the hex. So this 0x means it is a hex number, and after that we have 64 entries for a 32 byte number. Okay, and in this case we have 0x here, that is denoting the hex, and then we have 63 zeros, and we have the number 2. Now in the case of 10, we have 62 zeros and 0a as a number, because in the hex we have 10 denoted as 0a. Okay, I think this is starting to make some sense. Sorry. Okay, I think it will start to make sense in just a bit, and don't worry, don't worry. Now, let's say we have different op codes. Let's say in the EVM, I push something, and the push. What does the push does? We can just go here. The push actually pushes one word on the top of the stack, right? But in the case of EVM, one word is about 32 bytes, right? So what push does in the EVM, it actually pushes 32 byte word on the top of the stack. And what does the pop does? As the word size is 32 byte, it will actually do the same, but it will actually pop out, take the top value out of the stack, and do some calculation on it. Okay, yeah, this was about this second part. This was pretty hard, pretty hard concept. Not pretty hard, but if you understand it correctly, you are a god. Now, the third one is basic operations. Let's say, uh, considering the stack of the EVM, we can do only two operations. We can do push or we can do pop, right? But let's take an example of addition of two numbers. So how EVM operates at the assembly level, this is actually a very low level example, but if you can understand it, you are just sponge. Now I push one onto the stack and then I push two onto the stack. What does the add instruction do? Add actually pops two values out of the stack. Those will be first two and then one, then 2 plus 1 will be 3, and 3 will be pushed onto the stack. Okay, so this is how the example works, and this was about our stack structure, how the data is stored on EVM in the stack architecture. Now, the other thing is about memory, and this is the thing that you will deal more with the memory and storage while writing Solidity smart contracts. Now, talking about memory, the memory is a volatile memory or a temporary memory where you can actually store data, but as long as the function is being executed, the memory remains intact. But as the function is executed and the transaction is executed, the data is actually deleted. Okay, so that is why that is why it is called volatile. This memory is a byte addressable. It means that you can use byte addressing scheme. So if you want to store something at 0x1 at first memory location, you can store it. If you want to store something at 100th memory location, you can store it by targeting the specific location in the memory. Now the maximum number of bytes that you can use in the memory are 2 raised to power 256. That is a standard. Now, and different assembly level instructions that are used to interact with the memory scheme are mload and mstore. Mload is used to load one word from the memory at some specific location, and mstore is used to store one word or save one word onto some memory location that is specified while calling the mstore opcode. So these are opcode. What are opcodes? Opcodes are simple words that can perform something on the data. Now, talking about the fifth and I think the last point about memory, we will just see this all of the details in action. So, as I said earlier, memory is hex style addressable. So again, everything in AVM is almost hex, right? So 0x is always hex. So this thing 00 represents 0, 01 represents 1, and so on. And in the 32, and just for example, and not for example, just for actually, just take a note that 32 with the base 10, or 32 in decimal system, is actually 0x20 in hex. You can just view it on Google, because there is a slight representation scheme difference in hex and decimal system, base 10 and base 16. When you see 0x20 in actually in the EVM, you will have to reconcile in the mind that it is actually 32, 32 in the decimal system, in the base 10 system. Okay, now in the EVM we have some special slots in the starting memory space. We have 0x00 to 0x20, it means the first 32 bytes, and 0x22, 0x22, 0x40, we have another 32 bytes. These two these two slots, so 132 byte word or 132 byte space, is called a slot in EVM. So the slot first and slot 2, uh, first and second slot are the scratch spaces, uh, that are not used by programmers, but they are used by the EVM to perform some hash calculations and all that. We cannot use them. And so what is the memory we can use? So at the pointer 0x40, 0x40 is the location, that is the free memory pointer. It is where we actually have a memory location address where we can start, actually where we can start storing data. For example, in the 0x40, let's take this example. The 0x0 and 0x20 are scratch space, we cannot use them. At 0x40, I have an address of the memory location where I can start storing some data. So let's say I have 0x80 stored here. So whenever I store a variable, let's say I store a variable called, that is an integer variable, that is uint 256 variable, and I want to store it. What will happen is Solidity or EVM will actually pull the memory location from 0x40, and that will be 0x80, right? 0x80, and the integer variable will be stored at 0x80, right? And now let's just for simplicity, let's take an example of you know take an example of storing the variable. The free memory pointer is 0x40, and it is pointing to 0x80, right? If 80 memory location, right? And I want to store a 2, that is an integer, and inside Solidity I will store it like u into 56 int, sorry, let's say age is equals to 2, and this 2 in sorry, this u into 56 will be stored at a memory location that is specified by 0x40. So what my compiler will do, it will go to 0x40 and see the latest memory location that is available to store my new data. So it will see 0x40 as the latest memory location. It will go to 0x80 and store the integer. Now the free mem pointer will be updated. Let's say it is updated to 0xa0. Now again, if I want to store some variable, the compiler will go again to the or the EVM will go again to the memptr free memory pointer, and it will see that the latest memory location that is available to write is 0xa0. So it will just pick this location and store my new variable at this location, and then free memory pointer is updated again, and this will go on. So this was the lengthy part of this video, and it was about memory. The other thing is called storage, and this is something you will deal a lot more with. in Solidity when you are declaring variables in smart contract that are permanent. So storage is a permanent data storage method, and that is even byte addressable, and the maximum size is 2 raised to power 256 bytes. You cannot store more than 2 raised to power 256 bytes of data in storage. We can use not we can actually we use two methods to interact with the storage of the smart contract, and those are sload and store. So what does sload does? We give a memory location to sload, and it actually get the data at that memory location in the storage and loads into the stack. What store does is we give some value and some memory location in the storage to store the data on. Yeah, that is pretty much about it. And in the storage, we know that it is unique to every smart contract, and but unfortunately it is the expensive way to store data. We actually either store the data in memory or call data, but for permanent stuff we use storage. So that was about storage. We are almost there. If you have made it till now, just give a pat on your back. You have done a great job, seriously. And yeah, the fourth part is about call data. So what is a call data? The data that is passed to a function when we want to execute that function. Let's say I want to execute a function called hello, and I pass a string called greeting message. That greeting message is now a call data. Okay. Now this call data is read only, and it is a temporary method of storage of data. After the function is executed or transaction is executed, this data will be vanished. This is a very cost effective way to store data, or a cheap method to pass data. Okay. Because it is effective in terms of gas. We will see it in the details in the next videos. And again, it is unique to every smart contract call. Okay. And every unique smart contract call or function call, it will be unique. Yeah. And for logs, so what are logs? These are the messages by smart contract when the state changes. Let's say I mint an NFT, and that NFT is minted on my name. Initially, that was not owned by anyone, but now it is owned by me. So there will be a log that is emitted. Now, EVM does not implement the logging by itself, but as a programmer, we have to write it in Solidity. Now, when we write different smart contracts, we want to we want to make our smart contract or write our smart contract in a way that is actually interoperable with the real world. Let's say, uh, let's say let's say Bob has an NFT and he owns the NFT. Now, if if the NFT is transferred to me, then there will be a log that is emitted to me. And now, let's say I have a DApp, I have a app, Web3 app that is actually, uh, you know, that is actually providing some rewards for owning that NFT. Now, Bob does not own that NFT. I own that NFT. So the rewards should come to me. But how does how does the outworld Web3 app will know it? It will have an event handler that is tied to our smart contract. So if the transfer event is emitted, if the transfer event or log is emitted from our smart contract, this app will see whom to send the funds. So this is a pretty good use case where we use the logs. It is a permanent data storage. It is tied to every very unique smart contract, and but it is only read only. You cannot rewrite the data to a log, and it is used for outside world interaction. And we have some indexed fields. We will see it in our Solidity tutorials. And let's just quickly go through the indexed fields. Then The indexed field method is used when we want to make our logging searching faster. So let's say I have thousands of logs, but I want to search some specific data. If that data field is actually indexed, then it will be pretty easier for me to search that data, because it will be indexed and there will be some benefits to it. We will see it in the next video. So this was about the fifth data storage method. We have done a lot. We are just close to completing it. Just give another pat on your back. Okay. The other or last method to store data on EVM smart contracts is the code. Let's say we have different constants or immutable variables that we don't want to change in the. I think those are the just constant variables, right? So let's say I have some constant variables. Let's say like pi is equals to 3.14, and let's say 3, and I don't want to change it. So what Solidity will do, or EVM, what happens in the EVM is, instead of storing pi in the storage, we will, on compile time, when we are compiling a smart contract, the pi, every instance of pi variable will be replaced by 3, actually itself, 3 itself, and there will be no variable pi. And if there is some calculation like pi multiplied by 78, then this will be replaced in the code by 3 multiplied by 78. This will actually, uh, this is very cost effective, first of all, and this will save a lot of gas from our end. This is a permanent method to store the data, but this is read only, and the data is actually stored in the bytecode, and that is unique to every smart contract again. So that was much about our video, and I hope you have got a lot of value. But wait a minute. We have the most important part left, and that is the part that most people don't understand really well. So I want you to be in the 1% club of the blockchain developer era. So let's quickly go through this, and we will then together celebrate the party. Okay. Now, what is Ethereum gas? So, Ethereum gas is just a unit that is required to do some work on Ethereum. Let's say you have a vehicle, or let's say you have a car, and that is that works on petrol. If you don't have petrol, it will not work. So even in the real world, we need some commodity, we need some stuff to work on, right? So if I don't have petrol, that if I don't have petrol, the vehicles will, go on and on. They can go anywhere, right? And that is not realistic. And even okay, so this can happen on Ethereum, that we don't have any gas limitations or uh, any commodity limitations on Ethereum. But there is a problem. Ethereum itself is Turing complete. So what does Turing complete mean? Turing complete means that it can mimic the behavior of the outside world, given enough computation and all that. Now, Turing completeness introduces loops. So those loops can run indefinitely. Let's say I have a loop, and due to some miscondition, I have this loop that is running thousands or millions of times instead of just one or two times, and that will actually halt the entire EVM, right? And due to this reason, anyone can actually make a transaction that can halt the entire EVM, right? So there can be a denial of service or DDoS attack. And to prevent this, Ethereum has introduced the concept of gas. So to perform every calculation on Ethereum, we need to actually pay some amount of gas units. So the gas units will not be infinite to any user. So there will be very 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 less chances of DOS attacks. So how gas works, while performing any calculation on the smart contract, the smart contract logic is decomposed into the byte codes, and each byte code, sorry, and the byte code actually contains the op codes, and each op code has some amount of gas that is required to operate that. Let's say add, or let's say mload, mload opcode. uh, these opcodes actually, uh, what would I call it, these opcodes actually require 2 to 3 gas units, right? So if I want to run a transaction that that you know that wants to halt the EVM, then I need to have the millions or infinite amount of gas, and that is practically not possible. So this was the concept behind Ethereum gas, so that the Ethereum don't face the denial of service attack. Okay. Okay, so that was a lot about Ethereum gas. Now the other one, the last topic that we want to discuss here is about message calls, and after that you will be free. Now, what are the message calls? So whenever we want to actually whenever we want to interact with someone, we can call someone, or we can message someone, right? In the blockchain world, whenever a smart contract interacts with the externally owned account, or externally owned account uh, interacts with the smart contract, that is actually called a message call. And that message call can involve either sending some funds, sending some ether, or calling some functions of the smart contracts, right? So in case of sending ether, the message call is really straightforward. We just send some ether. But in case of function calls, we have we need to provide some arguments for the function to execute, and there will be some return data. After execution of that function, there will be some return values that is returned by the function to the caller, right? So the arguments will be called the payload, and the return data will be called return data. And now, in when we are making the function calls, we are sending arguments and payload, right? And there are two types of function calls. There are static and delegate. So whenever a contract or an externally owned account is making a call to a contract, there will be two types of there can be two types of function calls. One can be static. In static, there will be a separate storage of the function, or sorry, there will be a separate storage of the contract that is being called. Let's say I call a contract of Bob, and not Bob. I call a contract A. There is a function called hello. I call the hello function of the contract A. The contract A has a separate storage, and it will not modify anything outside its storage. But let's take an example. If if I call a contract A, and there is a function called hello, and inside hello I call another function of contract B, and contract B, and that uses delegate call to you know delegate call to call that other contract, you know other contracts function. then there will be uh, then there will be a storage of that contract, but that storage will not be a separate one. That will be storage of the caller. Now this is getting quite complex. Now let's quickly understand with the example. So in the static call, we have contract A, and we have some variable called counter one, and I call this contract call the function one of contract B, right? Before call, the storage of A has counter one and storage of B has counter one. After call, because it is just a static call, there will be no changes in the storage of this caller contract, right? So after call, there will be only changes in the contract that is called, right? That is contract B. Now after call, the storage of A will remain same, the storage of B will change. But here is an interesting part about delegate call. Delegate call changes the uh, sorry the delegate call The delegate called contract changes anything in the storage with respect to or in the context of the contract that has called it. Okay, let's just understand with example. Before call, storage of A is counter is equal to 1 and storage of B is equal to counter is equal to 1, right? When I delegate call it, when the contract A calls the function of B contract with the delegate call, the counter is updated. Now this counter is not updated according to this storage, but this counter is updated according to the storage of the caller contract, right? That is A. So after call, the storage of A, in the storage of A, the counter will become 2, and in the storage of B, the counter will remain same. I know this is a lot to understand or comprehend, but this was a lot to digest. And if you are still with me till now, then just I really appreciate you because there is a ton of value that is packed inside this video, and I hope you will like it. And just pardon me for my stuttering voice because I have not recorded a video like this before, but I hope you will get a lot. You have gotten a lot of value. If some concept is not if you were unable to understand any concept, I would highly encourage you to watch the video again one time or two time again. And if you still have some issues, just shoot a DM on Twitter or LinkedIn, and I will list my social media accounts in the description. And yeah, I hope you have enjoyed the video, and see you in the next one.